Okay, this is one of these sort of word problems that McMurray likes to use that uh, ask you to get a little creative and use the molecular formula and a little bit of a hint or two to come up with a structure. So propose structures for the following. We have a ketone and its molecular formula is C4H8O. C4H8O. Now, 4 carbons and 8 hydrogens and an oxygen. So if we have 4 carbons, we can put them in a row like this. And it's a ketone, so let's just make this a ketone. Let's put the C double bond O here, and then count the number of hydrogens. 1, 2, 3, 4, 5, 6, 7, 8. So this is a match. So that's A. Let's look at B. C3H9N. Okay. So this is a nitrile. So a nitrile is a C triple bond N. So that's a nitrile, and I'll put a little squiggly line there that says something else is on the other side of that. You can also say R. And then the R has the rest of the molecular formula in it. So if we have a CN here, and I'll put my lone pair there, we need 2 other carbons. So what's left is, what remains is C2H9. And we've already taken care of, oh, sorry, this is C5. So that's C5. Got that wrong. So what remains is C4H9. Now, how can we have 4 carbons and 9 hydrogens? Well, let's see, 1, 2, 3, 4, 5, 6, 7, and then if we put our CN out here, that will give us 1, 2, 3, 4, 5, 6, 7, 8, 9 hydrogens. So this is C5H9N. Okay, so that works. Let's try another one. So move these over. Whoops. So move these guys, shrink them a little bit, and move them over. And C, a dialdehyde, C4H6O2. And that is a dialdehyde. So that means that there are 2 of these functionalities. Something like that, where we have COH, that's the aldehyde is CHO, CHO. So the rest of the molecule, if we subtract 2 CHO groups, that would give us minus C2H2O2. So if we subtract C2H2O2 from this, that leaves us with C2H4 and no oxygens. So C2H4 would have, let's just see, there's 2 carbons there, and then I'll draw in the hydrogens, H4, 1, 2, 3, 4, and then we can attach our aldehydes here, like this. And now if we count them, we have 1, 2, 3, 4 carbons, so this is C4, H, 1, 2, 3, 4, 5, 6, H6, O2. So that is our dialdehyde. Okay, so let's try another one here. And if I I move all of these to a, oops. If I move all of these to a different layer, that might make things a little easier. So I'll cut that, and make a new layer, paste it, and shrink it down a little bit here. Okay, so D is a bromoalkene with the molecular formula C6H11Br. So a bromoalkene means that there's a bromine and a double bond. So if we have C6H11, let's just put 6 carbons in, 1, 2, 3, 4, 5, 6, and then, I don't know, let's just put an alkene somewhere in the molecule, right here. And then let's add a bromine. Why don't we add it right here? And let's just count the hydrogens and see where we are. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this C6H11Br works. If I had done it like this, I could have just as easily said, okay, we have an alkene. I'll put an alkene over here, and let me just put a Br down here. Let's see if that works. So 6 carbons, 1, 2, 3, 4, 5, 6, C6, H 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, H11, and then Br. So that works too. Both of these actually work equally well. Whoops. Having a little trouble here. So let's go to E. E, an alkane, C6H14. C6H14. All right, well, if we just try to draw 6 carbons and then count the hydrogens, let's see what we get. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So C6H14. That was easy. We could have done it like this. We could have made it branched. So 1, 2, 3, 4, 5, 6. That's 6 carbons. And if you count the hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So both of these work. And there are other ways to make branching hexanes. Let's look at F here. So F is a cyclic saturated hydrocarbon. So C6H12, it's cyclic and saturated. That means that it has a cyclic structure. So let's just draw 6 carbons in a cyclic structure like that. And saturated means that it has no double bonds. So let's count the hydrogens. 2, 4, 6, 8, 10, 12. So that works. Cyclohexane. And G, C5H8, a dialkene, C5H8. That's a diene. So let's do 1, 2, 3, 4, 5 carbons. And I don't know, let's put two alkenes in, 2 double bonds, 1 there and 1 there. That's 1, 2, 3, 4, 5 carbons, and 3, 4, 5, 6, 7, 8. C5H8. We could have put the double bonds on the 2 ends like this. This also has C5H8. The same molecular formula. And finally, a ketoalkene, so H, try this color, C5H8O. a ketoalkene. That means there's a ketone in it somewhere with R groups. I'll say R and R prime, meaning they don't have to be the same. And it has a double bond in it somewhere too. So let's just put a double bond in an alkene somewhere on a 5-carbon chain. So an alkene here, and why not put the ketone, I don't know, here? And let's see if that works. 1, 2, 3, 4, 5. So that's 5 carbons, C5. H, 1, 2, 3, 4, 5, 6, 7, 8. H, 8, and then there's an oxygen. So that works. You could have also had the double bond in the middle here and the ketone here. Why could we not have the ketone at the end like that and a double bond there? Well, that's not a ketone, because if it were at the end, if it were like this, that is an aldehyde because it has an H on the end. It has to have 2 carbons on either side of the ketone to be a ketone. Otherwise, it's an aldehyde if it has an H. Okay.